This video will cover 3 examples of linear application problems: rectangle or geometric, a mixture problem, which is chemistry, and a distance problem. Anytime we solve a linear or any application problem, we want to follow a few steps. First, we want to read the problem all the way through. And we may actually have to do that more than one time. Next, we want to draw a picture. This is a good way to identify your variables. If you can't draw a picture, you're still going to identify your variables. This is a really important step, and a lot of times people try to go directly to the third step, which is to write your equation. So keep in mind, if you do those first 2 steps, writing your equation is going to be much, much easier. Once we write the equation, we're going to solve. And then the last step, we're going to answer the question that was asked. And we should do that in a full sentence. And we do that to make sure that we've actually answered the question. So let's take a look at this first example. It says, a farmer plans to create a rectangular corral with 90 feet of fencing. One side of the corral will be the side of a barn, so no fencing will be needed. The side parallel to the barn is 40 feet more than half the other sides, the ones that are perpendicular to the barn. Find the area of the corral and use proper units. So I'm going to draw a picture here. I'm going to say that this is my barn. This is the side that's the barn. And then I'm going to have a rectangular pen coming off the side of that barn. So this is a nice picture, and this is going to kind of help me see what's going on. And you should notice that when we talk about the side parallel to the barn, we talk about it in terms of those other sides. So what we want to do is label those other sides. I'm going to call those X. And then the side parallel is 40 feet more than half of that side. So half of that would be half of X. And then 40 feet more would be plus 40. Okay, well, what else do we know? We know that we have 90 feet of fencing. So if we add these sides up, X plus 1/2 X plus 40, we should get our 90 feet of fencing. Now, we're not directly going to find the area. That's going to be what we answer as our question. But this is the information that we're given. So solving this, we will add our x's. So 1x and 1x and 1/2 x is 2.5, or 5/2 x plus 40 equals 90. We'll subtract 40, so we get 5/2 x equals 50. And then I'm going to get rid of this fraction, multiply by the reciprocal, 2/5 on this side and 2/5 on this side. So these cancel. We're just left with x. 5 goes into 50 10 times, and 10 times 2 is 20. So this is not the answer to the question, but it does tell me what x is. So now I know that this is 20 feet. This is also 20 feet. And if I plug in 20 here, 1/2 of 20 plus 40, we're going to get 50. So we have this rectangle. I'm going to redraw it here. Here's my barn. And here's my fencing. And it's 20 and 20. 250 feet. So now we're ready to answer the question, and the question is find the area of the corral. So area is length times width, and in this case 20 times 50, which will be 1,000, and the units should be square feet. So we're going to say the area of the corral is 1,000 square feet. Problem number 2 here is what we call a mixture problem. This particular example is a chemistry problem, but you can also use this for investments, this whole idea. So let's read the problem. A pharmacist is to prepare 15 milliliters of special eye drops for a glaucoma patient. The eye drop solution must have 2% active ingredient, but the pharmacist only has 10% and 1% solution in stock. How much of each type of solution should be used to fill the prescription? So when I do a mixture problem or even an investment problem, I like to think about what I'm doing. I've got some sort of 10% solution. We don't know how much. We're going to add that to a 1% solution, and we want to get a 2% solution, and we know we want 15 milliliters of that 2% solution. So whatever this value is, however much we have of the 10% solution and the 1% solution, those two have to add. Let's think about that for a second. They have to add to 15. So what we could do is subtract the x, 15 minus x, and call this x milliliters, and this one what's left, which is 15 minus x milliliters. At this point, we're going to take 10%, which is 0.10, and 1%, which is 0.01, and 2%, which is 0.02, and multiply them by their respective amounts. So for this container, I'm going to have 10% times x. This is going to be 1% times 15 minus x. And this last one will be 2% times 15. At this point, we use algebra to solve. So 0.01 times 15 is going to give us 0.15 minus 0.01x, we're just distributing. 0.02 times 15 is going to give us 0.3. Adding like terms, we get 0.10x minus 0.01x, or 0.09x. If I take 0.3 and I subtract 0.15, I'll get 0.15. And then I will divide by the 0.09. And we will get x equals approximately 1.666. I'm going to change that into a fraction. 5/3 milliliters. So that's x. That's how much we have here of the 10% solution. If we find out what 15 minus 5/3 is, we're going to get 13 1/3, or 40/3 of a milliliters. That's going to be your second solution, your 1% solution. And then we're going to answer our question. The pharmacist should use 5/3 milliliters of the 10% solution and 40/3 milliliters of the 1% solution. So I did say you could use this for investments as well. Something there might be the percentage percentage return that you're going to get, and then rather than the number of milliliters, it would be the amount of money you're investing. Our third example is a distance example. And we do need to know the distance is rate times time. So let's read this problem. A runner starts at the beginning of a runner's path and runs at a constant rate of 6 miles per hour. 5 minutes later, a second runner starts at the same place and runs at a constant rate of 8 miles per hour. So we want to know a couple of different questions, part A and part B. But before we do anything, you should notice that this is in miles per hour, and this is in miles per hour, and we have minutes. So we're going to change our 5 minutes into 5/60ths of an hour. Since there's 60 minutes in an hour, 5/60ths of an hour. So when I'm doing this kind of problem, I like to do a table. So I'm going to go to the bottom of the page here, and I'm going to make a table. And that table is going to be a distance, rate, time table. So I'm going to have runner number 1 and runner number 2, and we'll have distance, we'll have rate, and we'll have time in hours. And we want to fill this table in. So let's go back. We know that runner number 1 is 6 miles per hour, and runner number 2 is 8 miles per hour. So that's a rate. 6 and 8. Now, if you think about this, runner number 1 starts, and then 5 minutes later, runner number 2 starts. So in terms of time, I can say that runner number 1 is going to run for t hours, but runner number 2 isn't going to start for 5 minutes, so it's actually going to go t hours minus 5/60ths of an hour. Now, we know distance is equal to rate times time. I'm not given any information about distance, so I have to use my table to fill it out. I'm going to multiply rate times time and get 6t. And rate times time here is going to give me t minus 5/60ths. Okay, so now we have this nice table, organized our information. Let's go back to the questions that were asked. The first question is, if they're running in opposite directions. So I'm going to say that this is where we're starting. Runner number 1 is going a certain distance, and runner number 2 is going a certain distance, and we want that total distance to be 24 miles. So we're going to take these two distances from our table, 6t and 8 times t minus 5/60, 6t, and we're going to add 8t minus 5/60, and that's going to be a total of 24 miles. So now we need to simplify. So we'll get 6t plus 8t minus, when I distribute here, 8 times 5 is 40, and 40 over 60 is 2/3, equals 24. Simplifying further, 6 and 8 is 14t. If I add 2/3 to each side, 2/3 plus 24 is going to give me 74/3. You can use your calculator to do that. And then I'm going to divide both sides by 14, or alternately you can think of multiplying by 1/14. So the 14s are going to cancel, and we get t is equal to 1.76, and t, remember, we wrote it on our table, is hours. So we can say it will take 1.76 hours to be 24 miles apart. Okay, let's take a look at our second problem. We've already made our table organizing our information, but this one asks a little bit different question. It says, if they're going in the same direction, so we've got our starting point, we've got runner number 1, and we've got runner number 2, and the question is, when will the second runner overtake or catch up with the first runner? In other words, when will their distances be the same? So again, all we need to do is look at our table and set our two distances, 6t and 8 times t minus 5/60, equal to one another, because that would be when the distances were equal. So we have 8t minus 2/3. If I subtract 8t from each side, I get minus 2t equals minus 2/3. And I get t is equal to 1/3 of an hour. So now I can answer the question. The second runner will catch up with the first in 1/3 of an hour. We could also say 20 minutes, because 1/3 of 60 minutes is 20 minutes. But since everything was done in hours, we answer the question in hours. That concludes this video. I hope that helps. See you next time.